Previously, we have contrasted Weber's and Takagi's notion of class fields. Recall that Weber starts with an ideal group H with some modulus M, and he then defined the class field for H over K to be some finite Galois extension L over K, such that the primes that split in L are almost exactly the primes that split in H, with finitely many exceptions corresponding to primes dividing the modulus. Takagi, on the other hand, starts with a finite Galois extension L of K, and then define what it means for L to be a class field. According to Takagi, L is a class field if and only if the degree of L over K is gonna be equal to the index of some norm subgroup of L over K inside the fractional ideal group IM for some modulus M of K. This definition was inspired by Weber's generalization of Dirichlet's theorem. Recall that in Weber's generalization, we have that if L is a class field of an ideal group H, then the index of H inside IM is gonna be equal to the degree of the extension L over K. Takagi used this identity instead of the splitting law to define class field. For Takagi, L is a class field if there is a modulus M such that the degree of L over K is going to be equal to the index of some norm subgroup of L over K inside IM. Later we'll see that every subgroup of this generalized ideal class group is a norm subgroup. So the two definitions are not that different. Now, what is the norm subgroup of L over K? Recall that previously we have defined the notion of a norm of a fractional ideal of L. Then naturally, given a modulus M, we can define the norm group corresponding to M as the group consisting of all fractional ideal I, such that I is the norm of some ideal J in L and I is prime to the modulus M. This definition sounds good, but it has a problem. This group and M here might not be an ideal group, because this norm group might not contain Pm. Remember, by definition, an ideal group has to be sandwiched between Pm and Im. Therefore, to turn this norm group into an ideal group, a natural thing to do is to extend it by Pm. In other words, we can define the norm subgroup of L over K with respect to this module of M as the product of Pm with this norm group. Another way to think about this norm subgroup is that it's the unique ideal group whose image inside this quotient here is just a subgroup generated by this norm group. It turns out that every ideal group actually arises this way. For every subgroup of this generalized ideal class group, there exists a finite extension L of K such that that subgroup is gonna be generated by the norm group of L over K. Now, the significance of being a norm is that an ideal P of OK is a norm if and only if it splits completely in L. Therefore, even though L might not be the class field corresponding to the ideal group HM, we do know that the primes of L that splits over K must lie inside this HM because it must lie inside this norm group. And therefore, by the first part of Weber's theorem, we do have that the index of H inside IM must be less than or equal to the degree of L over K. Observe that equality happens if and only if the set of primes of L that splits over K is basically the set of primes in H, i.e. if and only if L is the class field of H. Therefore, L is a class field for its norm group if and only if this identity holds. Now we can show that if L is a class field, then it must be a class field for some norm group. And therefore, Takagi actually used this equality here to define the notion of class field. So L is a class field if there is a modulus M of K such that the degree of L over K is equal to the index of the corresponding norm group inside IM. So let us look at some example. Let us show that Qi is a class field over Q. To show this, we must find some norm subgroup HM such that the following identity holds. To that end, we're gonna let the modulus M be 4 multiplied with the canonical infinite prime on Q. Let us now find the norm subgroup of Qi over Q with respect to M. Observe that every fractional ideal in Qi is principal, therefore its norm is just gonna be equal to the ideal generated by the norm of this generator, which is just gonna be congruent to either 2 or 1 modulo 4. Observe that this generator here is also totally positive, and therefore almost all elements of this ideal must lie inside Pm. Therefore, we get that this norm group here lies inside Pm. Now recall that we defined the corresponding norm ideal group to just be the extension of this norm group inside Pm. Thus, since in our case the norm group lies inside Pm, this ideal norm group is going to be equal to Pm. And thus, the index of this norm subgroup inside Im is just going to be equal to the index of Pm inside Im. And then recall that this group here is just isomorphic to the unit group of Z mod 4Z. Recall that we did show that Weber's notion of generalized ideal class group is a generalization of Z mod mz star, and we show that if we choose the modulus m to just be the principal ideal generated by some integer m, then in that case the generalized ideal class group corresponding to Pm is just going to be isomorphic to Z mod mz star. Now, the same argument works for Takagi's generalized ideal class group, and therefore we have that this index here is equal to the size of this unit group, which is just 2, and thus this index here is equal to the degree of Qi over Q. This means in particular that Qi is a class field in the Takagi sense. Up next, we're gonna give an overview of what Takagi proved.